A $40 spinning cap on your roof can drop your attic 37 degrees and slash your cooling. Bill HOAs banned it for looking ugly. You've probably driven past one 1,000 times without thinking about it. A small spinning metal dome on the roof of an old farmhouse, a warehouse, a barn. The thing looks decorative. It's not. That spinning cap is doing more cooling work than the air conditioner you just paid $4,000 for. And it's doing it for free with no motor, no wiring, no maintenance, and no electricity bill at the end of the month. The reason you don't see them on new homes anymore has nothing to do with whether they work. The original 1,989 ASHRAE field study by J.D. Dale measured a 15% jump in attic ventilation rate from a single turbine, with peak attic temperatures dropping 10 to 20 degrees in real-world summer conditions. Pair that with a radiant barrier on the underside of your roof sheeting and combined drops as high as 37 degrees F show up in the 37 degrees show up in the published data. Those numbers come from peer-reviewed ASHRAE testing, not marketing copy. Your attic is the hottest part of your house every single summer afternoon, and the ductwork that runs through it loses between 20 and 40% of its cooling capacity by the time the conditioned air reaches your living room. That figure is from NREL and the Department of Energy, not from me. Your air conditioner doesn't just have to fight the heat outside, it's also fighting an oven sitting 2 feet above your bedroom ceiling. That's the case in roughly 70% of American single-family homes. So, a device that cuts attic peak temperatures by even 20 degrees F isn't a marginal upgrade. It's a structural fix. But here's the part most explanations skip because they don't actually understand what they're looking at. The spinning isn't the cooling. The spinning is just a side effect of 3 separate physics forces working together inside a 12-in piece of bent aluminum. Once you see how those forces stack, the 37 stops sounding like a stretch and starts sounding inevitable. The first force is Bernoulli's principle. When wind hits the curved vanes of the turbine, the air accelerates around the cowl, and accelerated air drops pressure. The faster the air moves over the top of the dome, the lower the pressure gets at the throat of the turbine. That low pressure acts like a vacuum on your attic. At a moderate 10 miles per hour's wind, you get about half a pascal of pressure differential, pulling hot air up and out through the turbine. Half a pascal sounds tiny, but it's enough to keep a continuous exhaust stream moving through a residential attic. The second force is stack effect, and this is the one most explanations get wrong. Stack effect is what happens when hot air rises because it's less dense than cold air, and the pressure that hot column creates can be calculated exactly. The formula combines the height of the column with the temperature difference between your attic and the air outside. Say when your attic is sitting at 150 degrees Fahrenheit and the air outside is 75, with the turbine mounted 4 feet above the attic floor. Stack effect alone generates between 3 and 4 pascals of pressure. That's 6 to 8 times stronger than the Bernoulli effect from a 10 miles per hour's wind, which means the turbine works even when the wind is dead still. The reason your neighbor's Whirlybird is still spinning on a 95 degrees windless day isn't because it's catching imaginary breezes. It's because the temperature difference between your attic and your yard is doing all the lifting on its own. The hotter the attic gets, the harder stack effect pulls. The hotter the attic gets, the more cooling load you'd otherwise dump on the air conditioner. It's a self-reinforcing loop where the worst-case condition for your house also happens to be the best-case condition for the turbine. That's why a working Whirlybird actually performs better at 3:00 hot p.m. in August than it does at 6:00 a.m. in June. The third force is the Venturi effect. Take a look at the turbine the next time you walk through a hardware store and count the vanes. Most have 28 to 32 curved scoops, and that geometry isn't random. The curved leading edge catches incoming wind from any direction, which is why the turbine self-orients without a wind vane. But the backside of each vane creates a narrow exit channel, and anytime air squeezes through a narrow channel, it accelerates. That acceleration creates more low pressure, which yank more attic air out, which makes the dome spin faster, which compounds the effect. This is the free pressure pump on your roof. Wind, heat, and geometry all stacking into one device with no moving parts, except the dome itself. Here's what those three forces actually do in numbers, because this is the part every other explanation of this device skips. A 12-in turbine moving at 5 miles per hour. Wind exhausts about 350 cubic feet of air per minute. A 14 model moves about 500. Your average 2,500 square foot attic at a 5 feet peak height is roughly 7,500 cubic feet of air. Divide that out. A single 12-in turbine is replacing the entire volume of air in your attic every 21 minutes. 520 minutes. That's 8 complete air changes per hour. Every hour the sun is up, the hot ductwork running through that attic is suddenly bathed in air that's 15 to 20 degrees cooler than it was before, and the radiant heat dumping down through your ceiling sheetrock noticeably drops. Your air conditioner stops fighting an oven on top of the house, which means it cycles less, which means your August electric bill stops looking like a car payment. Trade estimates put the seasonal cooling bill reduction between 10 and 20% in hot climates with attic ductwork. On a $350 August electric bill, the turbine pays for itself in one cooling season. Now, here is the part that nobody at the HVAC store will mention. If this device is so effective, why isn't there one on your house, your parents' house, your kid's school, your local Target? Why did an entire technology that was bolted to almost every roof in America from the 1950s through the 1980s suddenly disappear from new construction by the time we hit 2000? The answer isn't what you think. There is no industry conspiracy. There is no patent suppression. The Whirlybird was killed by your neighbor's homeowners association, and then it was buried by your local building inspector. Turbine ventilators are highly visible from the street. They sit on top of the highest point of a roof and they spin, which means the human eye locks onto them immediately. In the American housing market, real estate agents and appraisers consistently rank curb appeal among the top drivers of a home's resale price, and visible rooftop hardware like turbines, satellite dishes, anything that breaks a clean roof line gets flagged as a negative on listing photos and comp sheets. Builders chasing the cleanest possible, comparable on every spec home they put up, just stopped installing them. Ridge vents, which are flat, continuous strips that sit invisibly under the shingles at the peak of a roof, became the preferred alternative for one reason alone. You can't see them from the street. HOAs across the country wrote turbine ventilators directly out of their covenants in the 1990s. In Florida, where the heat load is so brutal that codes actually demand passive ventilation, the workaround is comically restrictive. State code lets you install a turbine, but only on the rear roof. Slope. The rear slope, which on most homes is the slope facing away from the prevailing wind. So the cheapest, most effective passive cooling device ever, invented for residential use, was relegated to the slope of your roof, where the wind hits it last and weakest. But the aesthetic ban is only half the story. The other half is regulatory. The International Energy Conservation Code, which most states have adopted in some form, and California's Title 24, specifically, both push new construction toward mechanical ventilation with controlled exchange rates. Mechanical means powered. Powered means a fan, and a fan means a motor, and a motor means a replacement. Schedule. A typical powered attic fan needs to be replaced every 5 to 10 years. It pulls electricity every minute it runs, generates a service called industry around it. A sealed bearing turbine ventilator, the kind that disappeared, has no motor, no wiring, no breaker, and a service life of 20 to 30 years if you keep the cowl out of the rain. There is no recurring revenue stream attached to a turbine. There is no annual maintenance call. There is no replacement schedule. Run the math on what that actually costs. Your neighborhood. A powered attic fan. Installation runs $6 to $1 when an HVAC company does it. The fan itself draws 300 W of electricity for as long as the thermostat tells it to run, which is roughly 1,400 watt-hours per cooling season. In a hot climate, that's 420 watts per year, just to power your attic fan. Or about $75 on a typical electric bill. The motor burns out around year 7, and replacement call costs another $400 to $600 in labor, plus the new motor. Spread across the life of the house, the powered vent costs you between $5,000 and $8,000 in installation, electricity, and replacements. The turbine in the same period costs you $40 up front, $0 in electricity, and $0 in replacements because the bearings are sealed and the metal doesn't corrode under normal conditions. This is the silent rooftop tax. Every house that gets a powered vent instead of a passive one is feeding the HVAC service economy on a 7-year repeat cycle. Multiply that by 70 million American houses, and you understand why no contractor at your local hardware store will ever recommend the $40 option over the $800 option. There's one more reason the industry quietly pushed against turbines, and it has to do with how they interact with other roof vents. If you have a ridge vent already installed at the peak of your roof, and you add a turbine ventilator 10 feet, 5 feet below it, the two devices share the same attic plenum and start fighting each other for make-up air. The turbine pulls harder, which creates a stronger negative pressure inside the attic, and the ridge vent reverses direction. Air that should be exiting your ridge vent now flows backward, sucking in outside air, dust, rain, spray, and in heavy storms, actual snow. Roofers call this short-circuiting, and it's used as the standard excuse for why turbines were always unreliable. The truth is, the failure isn't the turbine. The failure is the design choice to mix two passive vent types on the same roof. If you remove the ridge vent, or if you cap it where the turbine sits, the entire problem goes away. But explaining that nuance takes 60 seconds and a diagram, which is exactly the kind of conversation that doesn't happen on a sales call for a powered attic fan that costs 20 times more. You don't have to play that game. Now, here is where the build itself gets interesting. A 12-in turbine ventilator at any major Hardware store runs you between $20 and $60, depending on whether you buy aluminum or galvanized steel. The mid-range models, the ones with the sealed precision bearings, and the heavier 3/0 gauge metal, sit right around $40. A 14-in version, which moves about 50% more air, runs you $60 to $100. Installation is 2 hours if you've ever climbed a ladder. You cut a circle in the roof sheathing using the manufacturer's template. You set the flashing in a bed of roofing sealant. You drop the turbine base over the flashing. You bolt down the cowl, and you're done. Total parts cost, including flashing and sealant, comes in under $60. A roofing contractor will charge you $100 to $300 per unit installed, which is still less than a single annual service. Call on a powered attic fan. Then, there's the 2-unit rule. And this is where most homeowners get it wrong. A single turbine on a 1,500 square foot attic isn't enough. Your attic volume at 5 feet average ceiling height is 7,500 cu/ft, and a 12-in turbine at a 5 mils per hour. Breeze moves about 350 cu/ft per minute. That's 8 air changes per hour, which is good, but not enough to keep the attic ahead of solar radiation peak. You want to get to 5 or 6 air changes per hour during the worst of August, which means 2 turbines mounted at the high points of the roof, spaced at least 12 feet apart to avoid pressure. Balance interference, 1 per 750 sq/ft of attic floor is the working ratio. If you live anywhere south of Tennessee, run 2 14-in units instead, and you're done worrying about your attic for the next 2 decades. The placement matters as much as the count. Both turbines should sit on the windward slope, which on most American homes is the south or southwest slope, because that's where the prevailing summer wind hits. If your local HOA forces you onto the rear roof slope, accept the 20% performance hit and run a 3rd unit to compensate. 3 12-in turbines on the rear slope still move more air than 1 14-in on the front, and you keep the curb appeal. Cops off your case. Spacing those 3 units at least 10 feet apart prevents them from competing with each other for makeup air through the soffit vents. And while you're up there, check that your soffit vents actually run continuously around the perimeter of the house. A turbine pulling 350 CFM snorts out of an attic with blocked soffits creates a vacuum that ends up sucking conditioned air out of your living space through every crack in the ceiling. That's the failure mode that gave Whirlybirds a bad reputation in the 1970s, and it's not the turbine's fault. The turbine is doing exactly what it's supposed to do. The problem is the contractor who never opened up the intake side. But there's one catch that the Southern climate guides won't mention because it doesn't apply to them. Anywhere above the 40th parallel, which runs from Philadelphia west through Columbus and Indianapolis. And in Reno, you've got a winter problem. On a cold, humid night, the warm, moist air in your attic rises through the turbine and hits the freezing cold metal veins on the way out. That moisture condenses. The condensate freezes onto the bearing race, and by morning, your turbine is locked solid. The bearings can't spin, and worse, the trapped ice can crack the bearing seal. During the thaw cycle, the fix is a $30 accessory called an automatic turbine damper. It installs underneath your existing turbine and opens above 40 degrees drains, closes below it. No manual switching, no electrical. Hookup? No. November to April calendar. Reminder: the Southern climate guides don't tell You about it because they don't care. That's the whole device. $40. 3. Physics forces. A 20 degrees attic drop on its own. Up to 37 degrees when you pair it with a radiant barrier and a 10 to 20% cooling. Bill cut, paid back in cooling cost. Savings inside 3 summers. The only reason you don't have one is because somebody decided your roof needed to look like everybody else's roof. If a $40 spinning cap can rip 37 degrees out of your attic, wait until you see what a $300 dirt tunnel does to your entire house. If this breakdown of the physics and politics on your roof changed how you view home efficiency, please subscribe and like the channel. We are digging into the engineering secrets that have been hidden in plain sight. Let's build a more efficient future together. The next deep dive into the technology they don't want you to use is coming soon.